Okay, so hi everyone. So it's our pleasure today to welcome Wei Zhu, who will be giving the seminar this week. So just some brief background. So currently he's an assistant professor at the University of Massachusetts at Amherst. Prior to joining UMass as a tenure track assistant professor, he was a postdoc at Duke, and he received his PhD from UCLA in 2017 under Stanley Osher. He's generally interested in applied math, and he's been focusing on the mathematics of deep learning and data science. So today he will tell us about symmetry-preserving machine learning for computer vision, scientific computing, and distribution learning. So the floor is yours.
Thank you very much, Willie. It's my pleasure and it's my honor to be here. So today we're going to talk about, as William was saying, symmetry-preserving machine learning for computer vision, scientific computing, and distribution learning. And this is a sequence of joint work with a lot of amazing collaborators, and I will introduce them as we go on. Okay. So, well, the last decade, we have witnessed numerous success stories in deep learning with applications in, well, computer vision, game playing, autonomous driving, medical application, etc. Well, even though I think it's probably, I don't think it's necessary to talk too much about the background, but just for the sake of introducing the notation, so let's have a very brief review on what deep neural network or deep model is. So deep neural networks, whether it be fully connected or convolutional neural networks, can typically be viewed as a composition or concatenation of basic computational layers. And this composition will be called a function f with parameter thetas, which are the trainable parameters. And it is a function that maps a input x from the Euclidean space RDX to a output feature Kasi in another Euclidean space. For example, for fully connected network, then this f theta is going to be a concatenation of composition of linear and nonlinear operations. And given the input x, the first layer will be the linear operation that is essentially, well, affine operation. The parameter is going to be W and B, where the W is the weight matrix and B is going to be the bias. And the screen vector here is going to be W times X plus B. And after the linear operation, you typically have some nonlinear operation, which is usually the pointwise nonlinear activation that, well, that acts on every component of the screen vector. So every vector, for example, the ReLU activation will send every positive entry to remain the same, while the negative entries are set to 0. And after the nonlinear operation, we can call this second green vector here the first layer feature or first layer feature map. And the process goes iteratively goes on, and finally the model is going to spit out the output feature Kasi. And for this case, the fully connected network, this collection of trainable parameters, well, those B's and the W's will be the trainable parameter theta for the entire model. And well, given a machine learning task, typically usually in the supervised learning setting, this output feature Kasi will be fed into some loss function L that corresponding to a given machine learning task. And this L characterizes or measures some sort of mismatch between Kasi and the ground truth label Y of the input. For example, say if you have an image denoising task, then this X will be the input, the noisy image, and Y is the given label, which is the ground truth noise-free image. And Kasi is the output produced the model, and in this case, the L function, the loss function can be chosen, for example, as the distance, L2 distance between these two images. And when we say a trained deep neural network on a given labeled data, Xi, Yi pair sampled from some distribution D, essentially what we typically do is we try to minimize a loss function capital L, that is the empirical mean of the loss function over each pair of input. So essentially, this is small, or theta star is the optimal solution if the loss function here for each pair of input Xi and Yi, well, each output Kasi and Yi is small. And you would expect if you have more sample, then this empirical risk minimization is the process is going to be approaching the population risk minimization. And well, the problem is that, well, those black box F theta typically require a lot of abundant high quality data for the model to generalize. And what I will be talking about today is how to improve the data efficiency of the model by injecting some sort of structural information of the learning task directly into this F theta. And the structure that comes in that we will be mainly focused on is the symmetry, but more structure, other generalized structure will be also mentioned through the talk. So the first part of the talk will be on deformation-robust symmetry-preserving machine learning. And this is a sequence of work with collaborators at Purdue, Duke, and University of Washington, California Polytechnic, and UMass and Oregon State. Okay, so well, the reason why we care about the symmetry is because symmetry is ubiquitous not just in machine learning but also in scientific computing as well. Well, at least in computer vision, given the, say, if you have an image classification, then given the image of cat, then if you translate the image or shift the image by a certain pixel, then the label is still going to be a cat, meaning that the label function is invariant with respect to the translation of the input, or the label is a symmetry with respect to the translation. Similarly, if you have an image segmentation where you're given an input image, we want to, well, characterize or classify each pixel within this image. For example, pixels here will be classified as, well, automobiles, pixels here will be classified as road, and pixels here will be classified as tree and background, etc. Well, for this type of task, we would prefer the model to be to preserve symmetry as well, because if the input image is translated, you want the output image to be accordingly translated. And one of the reasons why CNNs are, well, arguably working very well in computer vision is because they preserve the translation symmetry, or they are translation equivariant. And to show this, let's say if you have an input image that is modeled as a continuous function in the continuous domain from R2 to R. So this R2 is going to be the domain for corresponding to the pixels, and each R2 is each point in R2 is going to be the coordinate of the pixel, and acts as a function that maps the kid pixel to its intensity. So here you're modeling a grayscale image. And the output after convolution, well, even though it's actually correlation, but in neural network community or in machine learning community, typically this is usually also called a convolution. But anyway, after some sort of convolution, it will give it an output. Convolution is essentially some weighted average locally at a pixel U. And then you can shift the output by some, or translate the output by a certain pixel V. This will give the result of the first computational chain. And on the other hand, you can also first translate the image by the same pixel V here, and then you convolve the image with the same filter. And we see that these two computational chains lead to the same result. That means, well, this diagram is commutative. And what it suggests is if you have a translated input, then after convolution, the output is correspondingly translated. And as I was saying, a lot of computer vision model would prefer, or computer vision task would prefer you have a equivariant model. For example, the previous case, you have image segmentation or motion estimation and object localization, etc. And well, for this type of task, we would prefer to model to preserve other type of symmetry. For example, the scaling symmetry. In this case, if you have an image, and if you rescale the image to a smaller scale, you would prefer the model to be able to automatically produce a output that is also rescaled by the same amount. However, those CNN, even though it preserves translation symmetry, it doesn't really preserve scale symmetry. And this is a very simple example. If you first convolve the image and rescale by some amount, you can also first rescale the image and convolve by the same filter, and these two results are not the same. So now the question is, how do you well, modify this type of convolution operation such that this diagram is commutative again? And this idea has been studied, well studied in the machine learning community, or how to build CNNs or neural networks that are equivariant to a certain group. And it was originally introduced by Cohen-Welling in 2016 for discrete group, that is, say, shifting on the lattice or rotating by 90 degrees or reflecting with respect to the axis of an image. And it has been extended to other groups, for example, rotation and spherical CNN, which are signals defined on a sphere, and you have SO3 rotation. And you can, well, extend it to permutation, especially working with graph neural networks. And it has also been studied for general theory and and also for scaling group as well. And well, what is usually lacking in those prior work, well, even though some of them have studied this before, is that there is limited theory that guarantees the stability of the equivariant representation. That is, well, if you know that the transformation group is perfectly defined, or the image or the signals are perfectly transformed through a symmetry group, then indeed those models can preserve such symmetry. But if your transformation is, say, contaminated by some other deformation not related to your group, can we still approximately ensure approximate equivariance in the end? All right, so before going to that, let's have a more rigorous definition of, more general definition of group equivariance. So given a domain X and a domain Y, and let's assume that you have some group G, that is, and you have two group actions, DG and TG, performing on the space X and Y. And we say the mapping F from the space X to Y is G equivariant if this diagram is cumulative. In the previous example, the mapping F is the convolution, and the space X and Y are both L2 functions, say on R2. And the group action here is going to be translation. And well, invariance is a special case of equivariance where you define the second group action to be the identity map. That means F is the same essentially across the group orbit transforming on the input. Okay, so with this definition, let's see how do we build, say, we'll focus on how to build a scale equivariant neural network. That is CNNs that, well, when I say scale equivariant, what I really mean is an equivariant model with respect to the scaling translation group. So this is going to be the semi-direct product between the scaling group S and the translation group R2. And S is essentially just R that corresponds to how much you want to rescale the image, and R2 corresponds to how much you want to shift the image. So let's have a comparison between the feed-forward neural network and the convolutional neural network and see what's the difference that makes CNN translation equivariant. Okay, so if you ignore all the nonlinear activation and the bias vector, then essentially the input at the L-1 layer feature map is going to be a vector in some dimension. And then to map from the previous layer feature map to the next layer feature map, you just have a weight matrix multiplication. So it's a matrix multiplication. To compute XL, you have a weight matrix and you multiply weight matrix by this vector to get to the next vector. And for this type of operation, all the spatial information is lost. Say if you originally have an image, you have to reorder it into a pixel, reorder all the pixels into a vector. So the spatial information is already lost. And to make the model to be translation equivariant, what you do is you sneak in another dimension U, or you preserve the dimension U corresponding to originally the spatial dimension. And it's not just a weight matrix multiplication, but instead the linear operation is going to be a convolution with respect to a spatial filter. So this time you have a convolutional filter that is defined on supported on the spatial domain, and to compute the next layer feature map, again, only looking at the linear operation, it's still going to be like a weight matrix multiplication in the unstructured channel lambda. Lambda can be corresponding to, say, the RGB channel of an image. But for the spatial domain, you have the spatial convolution. Okay, now if you want to, say, preserve the scaling symmetry, you can do something, something similar. That is, you sneak in another dimension alpha corresponding to the scaling group, and then you convolve this layer-wise feature map will be indexed both by U, the spatial domain, alpha, the scaling channel, and lambda corresponding to the RGB channel or unstructured channel of the signal. And you have some sort of a couple, the convolution between the feature and the convolutional filter. And this time, convolutional filter will be supported on both U and alpha. Okay, so we will talk about that later on as well. This is the so-called group convolution, which has been extensively studied, but in the scaling setting, it's actually very interesting. And there is some robustness issue and the numerical issue that we want to resolve as we proceed. Okay, so before get to that, let's just have a visual picture of what we want to achieve or how to build a scale equivariant CNN. So given the input image with the U corresponding to the spatial domain, again, the pixel location, and lambda corresponding to the channel, RGB channel, And you can define the group action on the spatial domain to be, you just shift the image by pixel v and then rescale it to 2 to the beta. So this is the input transformation. And then you want to build some neural network parameterized by the parameter theta, and it maps, the input and transform the input into feature maps. But this time you have an extra index alpha corresponding to the scaling group. And then you define, we define the group action on the output to be, for the spatial domain, it's similar, it's the same. You just shift the image by pixel v and then rescale it to 2 to the beta. And for the scale channel, there is a corresponding shift in the scale channel, and we'll see later on why there is this shift. Essentially, what you have here is it's going to be this is a group action that is the regular representation on the signal. And so the question is how we build this f theta. And it's fairly easy to see that if you have a feeder-forward neural network, with the regular feature representation that we defined. So it's the group action defined by the regular representation of the scaling translation group. Then this is equivariant if and only if, here you have the layer-wise operations are defined in such way. So here the sigma is going to be the nonlinear activation, for example, ReLU. So it acts on every entry. So in this case, it's act on every u with fixed u alpha and lambda. This sigma is just a function. And then to look at the first layer feature map, ignore the nonlinear activation sigma and the bias vector b. Essentially, what you're going to have is something that looks like very much like a wavelet transform. So essentially, to compute the response at the channel alpha, what you do is you convolve the image x naught with a filter that has been rescaled by 2 to the alpha. And this looks like a wavelet, but it's not really wavelet because you actually, wavelet is L2 normalized, but this time it's L1 normalized. And to compute the next layer feature map, you do some sort of a coupled convolution on both the spatial domain and the scale channel. And this is exactly the group convolution with respect to the scaling translation group, but write it down as the separated convolution over 2 domains. Okay, and let's look at the picture, what this architecture is actually doing. So essentially, given the input to compute the first layer feature map, this time, previously the input, you can view it as a 2D signal, but now this first layer feature map is going to be a 3D signal because there is another extra dimension alpha corresponding to the scaling group. And to compute the first layer feature map at the scale dimension alpha, scale channel alpha 1, what you do is you convolve the input with a filter that has been rescaled to 2 to the alpha. So this filter. And then if you want to compute the scale channel at alpha 2, you convolve the input with a filter that has been rescaled to another scale, 2 to the alpha 2. So this is the first layer feature map. And to compute the subsequent layers, you have not just the spatial convolution, but also the convolution with respect to, across different channels. So essentially, the information is not just propagating within each scale channel, but there is a vertical convolution corresponding to the scale channel as well. Okay. So, this seems all nice. We know how to build a scale equivariant neural network. But the question is, as I was alluding to before, in reality, the scaling effect is usually not going to be exact. It will be subject to some sort of changing view angle. That is, if you have original image, I exaggerated the effect a little bit, but given the original image, the scaling effect in reality is can typically be modeled by some deformation of the input and then followed by the perfect rescaling. So that means the scaling effect in reality is modeled as x naught. First, deform the input x naught by some deformation d tau operator. So this d tau is defined by, you first have some vector field tau, which is attached to each pixel in the domain. And you were deforming the image by, you're looking at x naught at u, but anchored at u minus tau u. So as you will see, as you can see, this tau function, if it's 0, it's always equal to 0. That means if you have a 0 vector field, then this d tau is just the identity map, meaning that there is no deformation. If tau is a small vector field, then essentially what you're going to have is a small local deformation performed on the input first before doing a perfect rescaling. And well, so now the question is, if you have some non-trivial deformation, so d tau is not identity, but it's still small, can we quantify the difference between these two computational chains such that, well, can we guarantee if this guy is small, then the distance between these two guys are small up to a certain extent? And the idea is fairly simple because, well, we know this d tau is the deformation on the input. So the idea is trying to filter out those deformation using regular basis functions. And this is inspired by a prior work by several of my collaborators. And so the idea is, given this convolutional filter, well, we know it's jointly supported on the spatial domain and the scale channel. What you can do is you first decompose the convolutional filter under these separable function bases. So for the spatial domain, we're taking is the Fourier-Bessel basis, which are eigenfunctions of the Dirichlet Laplacian supported on a unit disk on R2. And for the scale domain, assuming that the convolutional filters are compactly supported in scale as well. And what you can do is you take a orthonormal basis on the scale of these functions supported on the unit interval, and then you decompose the function, the filter under those prefixed basis functions. So previously, these filters are the trainable parameters of the model, but because these basis functions are fixed, so well, these convolution, the expansion coefficients will become the trainable parameters of our model. And to save computational efficiency or to improve computational efficiency or save model size, what you can do is you can truncate the convolutional filter, those basis expansion to only low frequency components. And a benefit of doing so is that, well, if you truncate the basis expansion to low frequency component, you can facilitate the robustness of the equivariant representation to those type of deformation. So essentially, by doing truncation of basis function, which facilitates the boundedness of the expansion coefficients, the boundedness of the Fourier-Bessel norm, which I will skip and not talk about too much of the detail, but essentially the message is, if this d tau is a small local deformation, meaning that those two norms are small with respect to the function tau, then these two distances should be still small. All right, so the model is still approximately equivariant, even if the input transformation is not perfect. Okay, so this seems nice. Well, you can deal with non-perfectly transformed group transformed input. So now the question is, well, if you have a scaling transformation, we know that we do have the scaling group is on the entire domain R. And if we, after convolving to produce, we have the first layer feature map, this should be a signal that is defined for each alpha. But however, when we're doing computation, we have to just keep the computation within a compact domain. So it's just supported on, so we have to truncate the signal to only a compact interval because we cannot keep computing to infinity. So what you're going to get is, after truncation of the first layer feature map, all the information beyond the interval is going to be lost. And then if you want to, well, move on to the second layer, then you have to do some sort of convolution with respect to the, well, this scale channel, meaning that those vertical information transfer will not be exact after such truncation. So now the question is, how can we, well, fill this information back into the picture? And the idea is fairly simple because, well, if we look at just the first layer of operation, this, as I mentioned before, this looks like a rivulet, but actually this is a modifier because this is L1 normalized, assuming that those W doesn't integral to 1, and assuming also the function doesn't integral to 0, and also assuming that the function x1 is, well, continuous enough with respect to the spatial domain, or smooth enough with respect to the spatial domain, then, well, this modifier approximation to identity will actually converge to the original function at the pixel u. So meaning that when alpha is getting smaller and smaller, at least in this direction, we can be sure that as long as the truncation interval is large enough, the information beyond the interval is still going to be close to the boundary. So this suggests that, well, we can just truncate to a large enough interval, and beyond that interval, you can just pad you can use padding according to the Neumann boundary condition, meaning that you just padding using the boundary value. And what we can show is that, well, if you truncate the scale channel up to some interval, say negative t to t, then you have some extra truncation error, but this truncation error is just exponentially decaying in t, assuming that the input is, say, smooth enough, say, in the Sobolev space. And well, then usually what people would do is just pad the information using zero value. In this case, if you have zero padding, then you have an extra truncation error that is O1. So instead of having O1, if you're padding correctly, you're going to have a truncation error that is exponentially decaying. Okay, and well, this of course works for scaling, but if you have some other group transformations, say if you want to preserve rotation symmetry as well, then what you can do is you can just sneak in another dimension theta corresponding to the group, say SO2. And then in this case, this separable basis decomposition is actually fairly useful because after basis decomposition, the convolution becomes all separable. So you can just convolve iteratively instead of figuring out the coupled convolution. And you can show essentially similar things. That is, the deformation is still going to be robust. If you have a deformation, the symmetry is still going to be robustly preserved. Okay, so let me just show some very simple numerical examples where you have multi-scale image classification. So the images we have are, well, rescaled MNIST and rescaled fashion MNIST. So it's scaled according to some randomly chosen number. And so here the first row shows the performance of a benchmark CNN. And this column corresponds to training using 2,000 images, and this column is training using 5,000 images. And this column ratio corresponds to what's the number of parameters of the current row compared to the benchmark. So what we can see is that, well, all those are scale equivariant CNN that we proposed, but truncated to different frequency components. So if you truncate it to low frequency components, you have a less expressive model, but the model size is smaller. And as we can see, say if you truncate it to this 5 components in space, 2 components in scale, then you can achieve still improved performance, but only using 10% of the original parameter. So you have a much smaller model size, achieving improved result. Okay, and well, what I was saying previously is mostly the, well, how to use symmetry for computer vision tasks, but actually symmetry is also useful for data-driven scientific computing. And well, typically, in particular, we can care about, say, data-driven solution of partial differential equations. Say here, you have, say, heat equation, and you have initial and boundary condition. And one of the method that has attracted a lot of attention recently, it's called a physics-informed neural network by these authors. And I'm using a picture from one of the paper, the DeepXT paper. Essentially, the idea is instead of solving this equation in the, well, traditional method, let's say finite difference or finite element, what you do is, well, you solve it in a data-driven way. So here you have the input coordinate xt, and you want a neural network to approximate the solution. So the neural network takes an input x and t, and it wants to spit out u hat that is very close to the solution u. And how do you measure this u hat is a good enough solution? Well, you just build a loss function based on, well, the L2, discrete L2 residual for the PDE and for the initial and boundary conditions. And then you train your model such that the loss is smaller and smaller, such that this U hat is getting closer and closer to the solution. And well, this is called a physics-informed neural network because you're putting the physics or the PDE into the picture to figure out how to data-drivenly solve this equation. But in a lot of cases, you will see that even though it's called physics informed, but if your training samples are not that many, then a lot of important physical information, in particular, symmetry information, is actually lost. So idea, or what I want to convey today, is that you can encode more additional symmetry information into the solution representation of this neural network, such that physics is somewhat better resolved, especially in the small data regime. And as an example, let's say you have this the so-called Abloix-Lardin model, which is a discrete counterpart of the nonlinear Schrödinger equation, but fully integrable. So for this type of model, we know a priori that the solution will have the PT symmetry, or it's time reversal, but in the spatial domain, it has parity, meaning that if you change the t, fix an n, it becomes the convex conjugate, and if you fix the t, but change with respect to the spatial domain n, and it's going to stay the same. In addition, what you also know is that for this type of solution, you have either space or time periodicity, just based on the knowledge of this differential equation. Okay, so if we can build all those structure, symmetry, and periodicity in the solution, can we really enforce the solution better, or can we train the model or solve the equation using much less training data? And as we can see in resolving some solution with the Kuznetsov-Mars-Soliton solution, here the exact solution is the blue curve. And if using the original pin, you will see that the solution, this is a fixed time slice of the solution. So it should be, well, taking the absolute value as well. So in this case, it should be symmetric with respect to space. And this green curve is not really symmetric, but if you enforce the symmetry and also periodicity in time into the solution, then the red curve is getting much closer to the exact solution. And similarly for other type of solution that is either periodic in space or periodic in time, but also preserve those PT symmetry, or S-pin, the symmetry preserved pin will perform much better compared to the original pin. Okay. So yeah, this is well, essentially want to say how symmetry can be used for predictive model, essentially in supervised learning setting. And now I want to shift the gear a little bit, but still closely related, and to talk about how symmetry can be used, not just symmetry, but actually general structure can be used in generative adversarial networks, so in the distribution learning setting. And this is a joint work with, and it's also ongoing, with Jeremy, Marcos, and Luke. All of those are my colleagues at UMass. Okay, so for the generative models that I will be talking about today is based on GAN, or generative adversarial networks. And since their introduction by Goodfellow et al., there has been a lot of innovative applications of GAN in distribution learning. In this case, well, say human face generation or animal face generation, or based on the text they want to generate image. And well, what are really GANs? Again, probably for this audience, it's not really necessary to talk too much, but just bear with me some basic introduction. So what GANs is that it's essentially a pair of neural network that tries to learn how to sample from, or learn to generate a probability distribution. And here, well, you can view this as a zero-sum game between, well, two players. One of the players is called a discriminator, and the other player is called a generator. And the game ends when the player reaches a consensus. That is, the generator is able to generate samples that look alike this original given sample or the real sample, and the discriminator cannot tell the difference between these two distribution. Okay, so let's put this into this picture. So what you have is some target distribution that you want to learn. So Q is unknown. What you only have access to Q is a finite sample of Q. And how to learn this distribution Q, what you do is that you have some random noise from some prior distribution. And then you have a generator, which is typically chosen as a neural network that tries to push forward the noise distribution to some generated distribution that is mimicking the distribution Q. So the generator is a good generator if PG is close to or PG is equal to Q. And how do you tell whether Q and PG are close? So this is where the second player, the discriminator, comes in. So the job of the discriminator is trying to tell the difference between these two distributions. And essentially what it does, it assign a value that is, say, close to 1 for a sample from the original given sample, and tries to assign a value close to 0 for the fake sample generated by this generator. And well, the model is, if Q and PG is getting closer and closer, then the discriminator can no longer tell the difference between these two. It's essentially assigning 1/2 to Q and PG. And mathematically, what you can view GAN is that you can view them as minimizing some sort of a variational divergence or some distance between probability Q and PG. So that is, you want to choose a generator G that can minimize some sort of distance between these two distributions Q and PG. And this distance is defined by taking the maximum of the discriminator gamma in the discriminator space, capital gamma. So it's kind of like the difference between Q and PG, or dissimilarity, is defined by a variational formulation by taking the test function or discriminator within some space. And indeed, a lot of GAN can be formulated in such setting. For example, the original GAN is essentially trying to minimize the Jason-Shannon divergence between two distributions. And the F divergence, or the F GAN, can include, say, the KO divergence, again, Jason-Shannon divergence. And the Wasserstein GAN is essentially, again, based on the gamma IPN, the Wasserstein distance, or the one Wasserstein distance. And you also have some other divergence, Wasserstein metric, Sinkhorn divergence, etc. Okay, so well, you have a very easy to understand probability distribution or probability measure learning setting. We want to approximate Q using PG. And now, well, in this setting, we typically do not assume any structure information in the Q. And to learn some arbitrary Q, you probably need a lot of samples such that PG is getting closer and closer to Q. So now if you know there is some structure information Q, can we use such information? And what are the structure information that we can use? Something that we can use is that, well, in many real world settings, the distribution that we want to learn or approximate is actually symmetric with respect to a group action. So, or it is invariant with respect to a group. For example, say if you have medical images taken without orientation preference, then the distribution should be invariant, say, to the rotation or reflection. What this means is that given the image on the left, if you manually rotate it by 90 degrees, then these images should have a similar probability, or they should have the same probability, or they should be equiprobable. So now the question is, how can we build such embedded structure into those two GAN players? One of them is generator, the other is the discriminator, such that we can have a more data efficient distribution learning, meaning that we can train the model using much less training data. And so now let's see, the setting becomes we want to figure out how to approximate Q such that the generate PG is getting closer and closer to Q in a variational divergence minimization setting, so the GAN setting, with the extra knowledge that the Q is invariant to a group sigma. And well, this sigma group can be, say, rotation, translation, or sort of group action that you perform on the input image or input distribution. And the idea, so now the question is, how can we incorporate such structure into the two players? And I want to mention that this work is inspired by the paper by Day et al. In the last year's ICM paper, in which they essentially build those discriminator and the generator to be invariant and equivariant model. And we want to explain why this indeed work. So before doing that, let's have just some to define two operators corresponding to some symmetrization with respect to the spatial domain, symmetrization with respect to the test function space, the discriminator space, and with respect to the probability space. So first, let's define what it means to symmetrize a function with respect to a group. So assuming that you originally have some function gamma that is a bounded measurable function on the space X. So in this case, the space X is going to be R2. And assuming that the group sigma, say it's the C4 group, so it's a rotation by 90 degrees. So this symmetrization operation applied onto gamma is essentially you try to average this. You want to shift the weight of this function across the group orbit, such that after symmetrization, this function, the test function, is going to be symmetric with respect to the group, or invariant after the group action. And similarly, you can define the do operation on the probability space, and the idea is the same. Given some sort of a probability measure, you want to shift the measure across the entire group orbit such that the probability measure is going to be invariant to the group. Okay, and it's very easy to see that these two operations, or these two operators, are projection operators. That is, if originally the function is invariant with respect to a group, then after symmetrization, it remains invariant and it remains the same. And for the probability measure, it's the same. If it's originally, it's a invariant probability measure. Invariant probability measure meaning that previously said, after rotating, the distribution is the same. And if it's originally invariant, then after symmetrization is still the same. Okay, so now let's see if we want to, how can we build such structure first into the discriminator? So let's first assume that we have already a good generator in the sense that it can generate a invariant distribution PG. Then how can we tell the difference between Q and PG using some sort of a smarter discriminator? How can you do that? Well, the idea is very simple. So assuming that you already have Q and PG that are invariant to a group, then to tell the difference between these two distributions, then essentially you just need to include those discriminators that are invariant with respect to those group as well. That is, well, you just need to assign the same value for images or samples from the distribution. So what we showed is that if you have two invariant distribution P and Q, then to tell the difference between P and Q using the original test function space is the same as telling the difference between P and Q with respect to the subspace of invariant discriminator. So here, this guy is a subset of gamma that includes only group invariant discriminators. And this is a much smaller space compared to gamma because you only have invariant discriminators, meaning that, well, you have two minimization and maximization. So in the max step, you have a very efficient GAN optimization because you're optimizing over a much smaller space. And what you're also doing is you're actually just placing a unbiased regularization such that you can prevent discriminator overfitting, which is a pitfall for a lot of GAN training. Okay, and there is a key assumption in this setting. We want essentially the gamma to be closed with respect to the group action, and it can be satisfied in a lot of general setting. And well, the second is, well, if we know how to design a smarter discriminator. So now how do we design a smarter generator such that it can generate an invariant distribution? And this idea is also very simple and has been studied before already, especially for flow-based method. The idea is, well, you can design some sort of random noise source that is sampling from a group invariant distribution. And then you design your generator to be an equivariant generator. Then you can guarantee the generated distribution is going to be an invariant distribution as well. So meaning that we can build such structure information and embed it into the smarter generator and the noise source. And the smarter generator and noise source, as we'll see in a moment, that it should be very important because it prevents mode collapse. So let's take a look at why these two and how these two are useful. So the first row, well, this is a example where we want to learn the distribution that is a mixture of T distribution. So it's actually embedded high dimension, but let's just look at the 2D slice. So we have 4 T distributions exhibiting C4 symmetry, again, so no rotation by 90 degrees. And if you use a traditional GAN, so there is no smart players involved, then you can see that it takes a long time to train and you actually need a lot of samples. And finally, the trained model is actually not really producing invariant distribution. And if you have both smart players for the generator and the discriminator, the generator is equivariant and the discriminator is invariant, then you can learn the distribution much faster and much better. So the interesting thing here is that if you only have the smart discriminator, meaning that the discriminator is an invariant function, but the generator is actually not a equivariant model, then you'll see that you will suffer from mode collapse. The learned distribution seems to be only sampling, say, one mode or two mode instead of equally sampling all those four modes. So what happens here? And the reason is also fairly simple, because previously we said if PQ is both invariant, then you can use the discriminated as an invariant as well. So let's assume now PQ are not invariant, then using a invariant discriminated space to tell the difference between Q and P is the same as using the original discriminated space to tell the difference between P and Q after symmetrization. Okay, so this explains what happens. So if this gamma, if you reduce gamma into invariant space of gamma, while this generated PG is not a guarantee to sigma invariant, then it only has to be equal to Q after symmetrization. So you can see here, well, because the generator is not guaranteed to be equivariant, so it's not generating invariant distribution. So it is just a slacking, and it is just the learning to sample from one mode because, well, after symmetrization, it is indeed sampling all those four modes. So essentially the message I want to convey here is that, well, if you want to build a smarter discriminator, then you have to be careful that the generator is also equally smart. Okay, and well, I don't have too much time to talk about, but this, you can extend this framework to beyond just the group symmetry, but also to other structure preserving operator. For example, this operator defined by a probability kernel, then we have something similar result. That is, you just need to include discriminators that are invariant with respect to the kernel. Okay, I'll skip this and just to take a look at, finally take a look at some numerical example here. I want to generate images that are the rotated MNIST data set. So you have the original image that are MNIST digits, and then you rotate it by a random degree. And if you use ignorant players, meaning that again, you just have the vanilla GAN, then the generated digits are not really that doesn't look good. And also there is not too much diversity within this rotation. And if you're using smart players, in this case, I just include C4 or C8 rotation symmetry, then you can generate a much better sample. And also there's a much diversity within this rotation. And you can also quantify the results using the so-called FID, Fréchet Inception Distance, which characterize how close the generated distribution is to the original distribution. And as we can see, well, you can almost have the smaller Fréchet Inception Distance, meaning that it is better, and it can achieve almost an order of magnitude improvement in at least measured in such metric. And the last example is for the medical image generation. Again, if you use ignorant player, then, well, the generated image is not really that, well, looks like the original real sample, but you have including more symmetry within your generator and the discriminator, then the generated images look much alike than the original samples. Okay, and I think that's it. Thank you very much for listening, and I'll be happy to take any questions.